first thing I want you to do is probably look up here. You remember probably seeing something like this about a year ago, or 2 years ago, now for one. And it's just for a quick second. It wasn't very long at all. So we're going to go over what these mean and try to refresh your memory. So it's more of a recall. There's going to be some new stuff, but mostly refreshing. So for instance, let's look at, here is the start of your homework. So state the domain and range of relation, determine whether it's a function or not, right, yes or no. So 3 things you have to do, domain, range, yes, no. Down here, it's tell whether it's discrete or continuous. That's new. You have graphs, and you have points, and you have an equation. So you have to know is it discrete or continuous by looking at any of the 3 representations: graph, points, also known as relation, or just an equation. On the next page, once again, graph each relation or equation, find the domain and range, determine whether it's a relation or equation, is a function, and state whether it's discrete or continuous. It's kind of the same questions on the first part. So there's really 2 parts. Everything up to here, 13 to 34, and then at 35 is a brief review of function notation. If the value of f of x equals 3x minus 5 and g of x equals x squared minus x, find f negative 3 and g of 3 and so on. This I like to equate with printing and cursive. This is a problem that you know how to do. You've done since probably the 7th, maybe 6th grade. It's just we write things a little different. So just think of it as the same problem you've always done. It's kind of the same words you always write. And you just sometimes you can write it in print, sometimes you can write it in cursive, but they're all spelled the same. And then the last set of problems are just from chapter 1. All right, let's go back. Oh, by the way, to be or not to be, that is the function question. What play is that from?
Hamlet.
Hamlet. Good. And what does this mean, to be or not to be? What is to be? What is that? Another word.
Something die, not to die.
To live or to die. To be, to live, or not to die. That is Hamlet Act 3, Scene 1. Let's see here. The actual objectives, we look at standards, analyze graphs. That's what all the domain, range, discrete, continuous stuff is. So this one little word packs in a lot. And at the end, just compare and contrast functional relations as opposed to non-functional relations. And we'll sum up what the importance of having a function means to us. So there's actually a good reason why we want to know if it's a function or not, besides just being able to complete your homework. A little vocab. Let's see here. Cartesian coordinate plane. You guys probably know it as a graph. X, y. That's all we're talking about. Nothing spectacular. Quadrants. This is fun because for some reason we still use Roman numerals to describe them. So that's quadrant 1. Quadrant 2. 3. Let's see here. What is relation? Set of points. Now when I say points, I mean ordered pairs, x, y. Points. Domain. It's usually the set of x values. And y is set of x values. For these, when you're writing your answer, please use this notation. Big D equals, and then braces. Because you notice how it says set. Set. This is set notation, right? Set of numbers always go in braces and range. So inside here, you can have some numbers like 1, 2, 3. You can have an inequality. All domain is every number that's greater than or equal to -1. Something like that. Or it could be all real. Sometimes domain is all numbers. So there's different things you can put in. Same thing with range. With range, it would be the same list of numbers. You can say all real, but of course, since range is y's, you wouldn't use x is greater than -1. You might say y is greater than -1. But it's identical for the other two. So just know, inside when you're doing this set, you could have points. You could have inequality. You could have 0. You could have an empty set. You could have no domain at all. Maybe an empty set. Resolution type of thing. A mapping. Remember what a mapping is. It's easier just to go back to the first page and say, this is a mapping. Right here. This is a mapping. It's another way of writing a T-chart, another way of writing a graph. And honestly, we don't see that too much. It's not something that occurs a lot. One thing to note is that any mapping can be written as a T-chart. We can take this and say, 3 maps to 1. Oh, that's 3, 1. 2 maps to 5. Okay, that's 2, 5. -6 maps to 5. Okay, -6, 5. So any mapping can be converted to a T-chart. Obviously, any T-chart can be converted to a graph. And also, any mapping you can also graph. So again, just think of these as looking at the same exact thing 3 different ways. Depending on whatever situation we're in, we might want to look at a T-chart or a graph. Maybe a mapping. Mapping is something we look at right now just a very little bit. In advanced math classes, you do a lot of mapping. And it's very abstract and out there stuff. It's after you finish calculus, after you finish most of the classes that involve numbers, you get into some really out there abstract stuff. Really talk about fancy things like homomorphisms and stuff like that. So there is a purpose for it. We don't look at too much of them right now, except for what's the main range? Is it a function? Okay, so that's a mapping function. When I say it's a relation, which means what? Relation is just a set of points, right? So it's a set of points where this is the technical definition. Each x, let's use the word has, only one y. And the word has, we can be more technical and say each x maps to only one y. But basically, each x has only one y, so the regular, everyday language we use. Okay. One-to-one function. It's similar to a function here. It's just it's a function, but also the reverse of this last part is also true. So a function is where one x has only one y. A one-to-one function would be each x has only one y, and each y has only one x. It would be this plus the reverse of this last underlined part. Each y has only one x. Really, not too important for us. It is in the book. It is there, but in calculus, very important. You'll see this over and over. It is the function on one-to-one. It's the function onto. There's another one. It's not in here yet. So I'm assuming everybody here is going to take calculus one day, so I'll give you these little previews, just so you know
when you hear me say this will be in calculus, this will be in calculus, when you get to calculus, you don't have this feeling like this is the first time you're seeing everything. It just all is connected. And again, continuous and discrete, I'll give you examples with graphs. It's a little bit easier to understand this by looking at graphs than just giving you a little definition. Okay, so far, really the most important thing on here I'd say is this notation for your graphs. For your answers, make sure you use this notation. Just like on your group quizzes and everything, if I said use set builder notation and you just didn't, like, well, there you have it. I'm telling you exactly what to do, and if you just don't do it, you know why? It's on video. I can pull it back and bring it up and when we did it. So don't make up your own way or shortcut way or your favorite way. Just follow everything. All right, so let's get into this fun stuff with function and not a function. Of course, we'll practice the other. Let's get this out of the way. There. Okay. So, what's the domain? 2 and 8. And how would you write it?
2, 21.
So, like I just mentioned, D.
Oh, D.
Equals. Yeah. Notice that there's no math involved here, but you can still miss the problem by not writing it properly. Right, so we're trying to teach you, get right answers, but also a proper way of writing your correct answers. If you don't write it properly, it's not going to be good. And same thing with range. We generally like to write these in numerical order, so put 2, 8, although 8, 2 wouldn't be confusing. It's when you get up to like 9 numbers and 10 numbers, we just kind of all randomly write them any way we want, instead of putting from least to greatest. It's kind of hard to check your answers. Somebody else's 2 is way over here, and 10 numbers, it's hard to track. So try to do least to greatest. All right. Let's see. What else would we want to know? Oh, can we write this as a T-chart? What would this be as a T-chart? The first one would be 2 maps to 21. That's 2, 21. 2 maps to 25. So that's 2, 25. And 8 maps to 30. Now the question is this a function or not? So your definition, does each x map to only one y? Only one. So each x map to only one y. Look right here. Here's an x. Does it map to only one y? No. It maps to 21, and it maps to 25. So this is not a function. Question?
Would it matter if you get the 8 to more than one y?
Nope, just takes one.
Okay.
Yeah, so as soon as one x is mapped to 2 y, it doesn't matter what's happening anywhere else.
Okay.
Right. Just takes one to one to make it not a function. How can you tell if it's a function or not by looking at the T-chart?
See repeated x's?
Yep, right here. That's the same idea. Each x maps to one y. Nope, this 2 is 21 and 2 is 25. So you're looking for repeated x's. So yeah, not a function there. So from a mapping you can tell because there's 2 arrows leading an x. And from a T-chart you can tell because there's repeated x. Notice how both of those explanations have nothing to do with lines. So while you're doing the function, not a function, you can ignore the range. You don't need any information. It doesn't influence that right answer whatsoever. You just need to look at the x. Is it repeating? Or are there 2 arrows leading one x, which is the same thing as repeating? That's how you can tell. Not too bad, not too bad. You guys go ahead and try this one. we'll just do this verbally since we're short on time today with the rally schedule. Domain is what?
D equals 3 equals 5, D equals 5.
5, 10, 15. Range.
R equals 105, 110.
R equals 105, 110, and braces, of course, for both of those. Now, function or not a function?
No. Wait.
Function. Does each x have exactly one y? Yeah, 5 has 105, 10 has 110, 15 has 105. Each of these x's has one y. Alright, and again, if you were fooled because you're looking over here at 105 and the 2 arrows, what did I tell you to do?
Not to.
Ignore that. Do you see 2 arrows anywhere? Okay. Okay. Alright, function. Now, sometimes it can be just a language thing, so listen very carefully. Yes, it repeats. So no, it's not a function. No, it doesn't repeat. So yes, it is a function. You might want to write that down because sometimes it can be confusing. You want to say, oh yeah, it repeats, so yeah, it's a function. Or no, it doesn't repeat, so no, it's not a function. You have it backwards. So yes, it repeats. No, it's not a function. That's number 1. And number 2 is, no, it doesn't repeat. So yes, it is a function. Okay. I'll trust you know domain range. Real fast about range on this one. Don't write anything that repeats. So you want to write zeros, or you want to write -2, -1, 0, 0, 4. You put -2, -1, 0, 4 if you're writing from least to greatest. So that's why I start with the negatives. But you don't want to write 0 twice. Just once is fine. So no repeats and domain and range. Probably want to write that down. Also, I want you to write things down that I say, not just copy what's up there. Sometimes the most important thing of the whole lesson is what I say and may not be up there. All right, beyond that, is this a function or not a function? And again, as soon as you come to that question, do this in your head or actually, cover it up with your hand in the book. Anything repeat? No, it doesn't repeat. Yes, it is a function. So it's always opposite, right? No, it doesn't repeat. Yes, it is a function. All right. Again. Nope. Okay. Aha. So, let's ignore the domain and range for now. Is that a function or not? Now, does each x have only one y? Or in other words, do any x's repeat? Or do you have one x that has 2 different y values right here? So let's draw a line there. And let's say this is the point, let's see, like maybe 5, comma, -3. There's 5 over, 5 to the right, down 3 is negative. What would the x value be right here? If it's right above it. It'd also be 5, because it's right above it. And we'll say it's 5, comma, 3, positive. Now, is it a function or not a function? Not a function. So yes, the x's repeat. No, it's not a function. So this is called the vertical line test. If the vertical line crosses a graph, it has to be completely vertical. Mine's a little crooked. But a completely vertical line, straight up and down, if it crosses a graph in more than 2 places, that means the x values are the same. Which means the x values repeat. Right. So, but notice how it's all the same thing, it's just they write them differently. But you're always looking for something repeating in the x's. X's repeat here, x's repeat here. On these, x's repeat. It's always what you're looking for. And again, I can ignore it. It doesn't matter what the y values are. I didn't even write it here because it doesn't matter. It's the fact that x's are the same, they repeat, not a function. Okay. So there's all the little nitty-gritty details of the main range, function, not a function. Okay, last piece about function, not a function. Why is that important? All right. In reality, I know we do a lot of abstract things to get a lot of right answers, sometimes without explanation. Usually, instead of x, we have t. A lot of times x in like science or something, it's time. We don't use x, we use time. It's always t, like minutes or hours or something. And then this could be any other variable. We'll use y anyway. But it could be like time, 1 hour, 2 hours, 3 hours. This is like, let's say, speed. Yeah, I'll use r actually. I'll use that. Distance, rate, and time. Yeah, r. Let's say r is 55. And this is, for 2, it's 65. You know, in 2 hours, we're going 65 miles an hour. 1 hour, we're going 55. In 3 hours, let's say we're going 60. This makes sense because every x has exactly one y. What wouldn't make sense, though? What if the mapping, okay, and at 1 hour, we didn't have this over here, and at 1, we have 55 and 65. What would that mean in reality? It would mean at 1 hour, we're going 55 miles an hour, and at the exact same time, we're going 65 miles an hour. Is that possible? No, it's not a function. That's why it doesn't make sense in reality. So anything that's not a function, you can't really use in the physical world. That's why we want to know what, if it is or isn't. Because if it isn't, forget about it. Don't need it. Okay? So that's the importance of this whole function, not a function. I know we just have a bunch of numbers. We're trying to memorize some basic rules to get a right answer, but that's the bigger reason. Things that are functions don't make sense in the physical world. We do have some other uses and some other aspects, but not in the physical world, like time and rate, things like that. Okay. I think we're doing pretty good with our function, not a function. Let's talk about, go ahead and do, you guys, on your whiteboard there, 1 through 3. You guys decide, and when they say vertical line test, that's function, not a function. So, vertical line test, function, question mark, is that function, not a function? Make sure you use the correct notation. One of you do the writing, and the other one, why don't you just be like the tutor and check over the shoulder to see if they're doing it correctly. Okay, so if we go ahead and plot these, 2, 3. I'm going to do this quickly. 2, 3, 3, 4, 4, 2. Is that correct? Here, 4, 2. And 2, negative 2. There we go. All right. There's our graph. Now, is this the graph? This is a weird question to ask, but is this the right graph for this right here? Yeah. Now, did anybody do this? Did you graph this and crazy line? Anybody do this and then go, okay, there we go, I'm going to connect those. Okay? So just make sure math is very specific, right? If it says plot those 4 points, that's what it wants. It doesn't want 4 points plus your own interpretation. Very, very, blunt about what it wants you to do, and if it doesn't say or tell you to do something, don't do it. So this is the proper graph. Don't make up any other line or something. Because imagine if I said plus crazy line, well, everybody can make up their own crazy line, and who's to say what's right and what's not? So another way of looking at it, well, should I do this, is that, well, if somebody else did it, would they get the exact same thing, or would it be completely different? If it's completely different, probably don't want to go there. Vertical line test. Is this a function or not a function?
Not a function.
Not a function, yeah, we can see that right here. Yes, the x's repeat. No, it's not a function. Vertical line test as well. So we could have seen that right from here before the graph. Domain and range, once again, write them out. Don't write any repeats. Lastly, discrete continuous. Here's the easiest way of looking at this. Continuous. Can you draw or plot the graph without picking up your pencil or your marker? Could you have made this without picking up your pencil, not even once? Could you made this exact graph with these 4 points?
Yeah.
So what do you think? Did you make these 4 points exactly without picking up your pencil at all? What do you think? Well, if I had to recreate it, I'd start right here, right? Wait a minute, can I make another point without picking up my pen?
No.
No, I'd have to go like this. Then I'd have to go like this. So this is not continuous. I'd have to pick up my pen each time to make another dot. This is not continuous, we're going to say it's discrete. So continuous is when you don't have to pick up your pen at all. It's continuous throughout the whole graph. Oh, it's discrete. Okay. And use that definition, write it down in your notes. Again, that's kind of an important thing. I want to know. Discrete. Here's the thing. There's no rule or anything I have for getting anything in here. Maybe it could be a curve. It could go this way, then this way. There's no rule for getting from one point to another. All we know for sure is these 4 points, and that's it. Nothing in between. Very discrete. Now, here's an example of continuous. Something like y equals 2x. Now, I know, okay, y equals 2x. That's kind of like up 2 over 1, up 2 over 1, up 2 over 1, and so on. So, I'm going to start drawing my graph. It goes like this. There's my whole graph. You notice how I didn't have to pick up my pen at all, and I can draw the whole thing. Minus these little arrows. So that would be continuous. I didn't have to pick up my pen at all, and I can draw the whole entire graph. Another way of looking at it is that I can plug in any points for x and get a y. So I can plug in 1, I can plug in 2, get 4, but I can also plug in every little decimal. I can get a point here, 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 here. You guys learned in geometry that a line is simply an infinite number of points. So I can plug in any little decimal fraction I can think of, multiply it by 2, and then it goes on here. That's another way of making sure if that happens everywhere, then it is continuous. And that's how you get a straight line. It's really an infinite number of points. Infinite number of points that make up a line. It is continuous. It doesn't matter. Here, I don't have anything between 2 and 3. I don't know what happens between 2 and 3. All I know is what happens at 2 and at 3, nothing between like here. Here I have 2, here I have 3. I also know every fraction decimal in between 2 and 3. Any smaller fraction you can think of, it's on that line. That makes it continuous. Now, rule of thumb for you guys for your homework, discrete, it's usually a relation. which is this, a set of points. They give you a set of points with, nothing in between, no information about what's going on between these points. That's discrete. You have to pick up your pen and make all the dots. And continuous, usually, those are the equations or the functions, for the most part. So on your homework, if you can see the question and they just list a bunch of points and ask you is it discrete or not, or is it continuous or discrete, you can use that rule. There are exceptions, of course. I'll give you a very simplified version, from the beginner's point of view. This will evolve over time. So there's your explanation of discrete and continuous. I can give you another example of discrete continuous. But the main thing on this problem that you're going to watch is how do you find domain and range of an equation? That's the main thing here. You guys know how to graph it. You know how to do vertical line tests. Now you know how to do discrete and continuous. The domain and range of a whole equation. You're not looking for an extra repeat or a, just list the numbers. You're looking for something a little bit more. Now this is a slightly different equation. Notice how it says y squared minus 1. Usually it was x squared minus 1, correct? So what we're going to do, what do you think would be easier to do? Pick some x's and find y, or pick some y's and find x's? Yeah, let's pick some y's. It's kind of opposite what we're used to, but a little bit easier because we can square the number and subtract 1 and get x. If we pick x's, we'd have to add 1 to both sides, take the square root of both sides, a little bit more involved. So I always like to use 0 in the middle, some negatives, and some positives. This is a very good practice anytime you're graphing. It might be tempting just to use all positives because they're easier numbers to plug in. You have to get over that convenience and say, well, something could happen in the negatives that I'm not expecting. Something could happen at 0 I'm not expecting. I got to try all 3 parts, negatives, 0, and positives. All right, so let's plug it in and get some numbers. Negative 2 squared minus 1 is 3. Negative 1 squared minus 1 is 7. 0 squared minus 1. And so on. 1 squared minus 1. And 2 squared minus 1. Notice how we get to symmetry like we always did before with parabolas and quadratics. It's just that the symmetry is in the x values in the domain instead of the y values where we're used to seeing it because we kind of switch where the square is. All right, let's go ahead and plot this. Any predictions of what this will look like? Will it look like a regular a parabola opening up, opening down? Or will it look different? Kind of looks similar, but there's, a little different. We'll start at the middle here. Negative 1, 0. There we go. 0, negative 1, 0, positive 1. 0, negative 1, 0, positive 1. 3, negative 2, 3, positive 2. Negative 1, 2, 3, negative 2, positive 2. Okay. First of all, is this a function or not a function? Look at the graph.
Not a function.
No, the x zeros. Anything repeating?
Yep. 0.
Yes, it repeats. No, not a function. Yes, it repeats. No, not a function. You can also do a vertical line test, like it says here, on the graph. You can get it from here as well. Now, discrete or continuous? So, is this graph, these points, does that encompass every single point of this equation? Or are there more points in between these that we just didn't do, for simplicity's sake? So, could I have plugged in like 1/4, 0.75, 0.3, negative 0.2? Could I have gone and plugged in all those as well and got an answer? Yeah, so that means if we wanted to, we could get all the points between them as well. This graph is not limited to just these 5 points and that's it. We just picked these because they're nice whole numbers and they're easy to calculate, mentally. But if we had to, like they had to way back in the day, the Newton days and Einstein days, they'd have to do all those by hand, and that's how they get the graphs. So yeah, this actually is a nice. I'm going to start right here. I'm going to plot it all the way around. So you see how I can do the whole graph without looking up the trend. That makes it a continuous function. And if you go by the rule I gave you earlier, it's an equation, so it's probably continuous. So that's it. That rule.
Not every time though, right?
Not every time, and there are a few exceptions. Not anytime soon will there be those exceptions, though. Okay. They have some discontinuous things coming up later. That'll be fun. Okay. Domain. Here's the fun part. Here's the new thing I really want to focus on. Domain. What are all the possible values of x here? Or another way of looking at it, are there any values of x that we do not have on this graph at all and never will have? So where do you not see the graph? Up here. Where are there no points at all?
On the negative side?
Over here. And where exactly? Starting where? Starting at -2 right here? Yeah, you see, starting right around here, there is no graph over here at all. There are no x values at all. So these are not in the domain. Starting at, what is this point again right here? That's -1. So everything left of -1 is not on the graph. Everything right of -1, including -1, is on the graph, right? All these x values have a y value right here. So everything starting at -1 and up, greater than or equal to, is the domain. Because these all have points on the graph. But nothing over here. -2, there's no points on the graph at -2. There's no points on the graph at -1.1. It's right next to -1. There's no points on the graph. So we're looking at only the x values and where there are points. Yeah. All the x values of this whole graph, if we plugged in any point for y at all, every single answer would be bigger or equal to -1. There's no number we can plug in for y we could choose that would come out to have an x that would be less than -1 because it's not on the graph. What about the range? Are there any possible values we cannot plug in here? Is there some number we're just prohibited to plug in at this equation right here? Is there anything we're not allowed to plug in and square it and subtract 1? No. So since there's no exclusions, everything goes. All real. Everything goes. And if you imagine extending this graph forever, except what these arrows mean, if we extend this graph forever, we could potentially say, well, we could extend this forever. We'll keep on getting smaller and smaller y's if we keep on extending this forever and ever and ever. In either up or down direction, right? So we can have any value of y. We can plug in any value of y, square it, and subtract 1. It's perfectly fine. Yes.
Wait, how do you know when to put, like, if x is an inequality, or when to just list what you float in each other?
Well, with continuous functions, you have to use this inequality. Because continuous functions have all these small points in between. We can't just say domain is, 3, -1, 0, 2, and 3, because all the little fractions and decimals in between those numbers also are technically in the domain. Good question. So discrete functions, you usually just say, 3, 0, 1, and so on. Continuous functions, we kind of have to use an inequality, or it's going to be all reals. Good point. Very good point. All right. Lastly, we'll do a quick review of this. This will be the last problem. This is the example I used earlier. It is like printing in cursive. Okay? Printing in cursive. This is like the cursive. The printing version that you guys have known for so long would look like this. Hey, if x equals 5, find out what x squared minus 3x is, right? And you plug 5 in here and 5 in here, and you get y. This is asking the exact same thing. Just think of it as this is printing right here, and this is the new way of doing it, cursive. There's one nice benefit about this. So this just means, again, this you read this, you know this, f of 5. That's how you say that. F of 5. That's how you say property. Don't say f parentheses 5. F of 5 equals, that means you plug in 5 for all the x's. You get 5 squared, x squared, 5 squared. 3 times 5. Equals 25 minus 15. Notice how it's the same exact order of operations you would have done back in the 7th grade if it was x equals 5 and plug it in. Here's the nice thing about this notation. What is the meaning of this? One is an x, one is a y. This is a coordinate. It's so much easier for graphing purposes to use function notation. I can go over here, do this several times over, build a nice t-chart, and have a nice graph. And at the end of my problem, I know this is x, this is y. This is a very good example of, I'll let you know later, of your inequalities. What does this mean? What does this mean? So at the end of this problem, you want to be able to say, what does this mean? It is a coordinate. Have a good weekend, everybody. Kuna Matata.